In today's video, we will be going over some simple first-order differential equations and some more specific cases involving initial conditions. For our first problem, we have been asked to verify that the indicated function is a solution of the given differential equation. For our first problem, we have been given the differential equation 36 times y plus the second derivative of y needs to be equal to 0, and the function we need to test is y is equal to 3 times the cosine of 6x. We begin by writing out the function we need to test. Y is equal to 3 times the cosine of 6x. It is then necessary that we take the first derivative of that function, and so y prime will be equal to negative 3 times 6, because of the chain rule, taking the 6x inside of our cosine function, times the sine of 6x, and this will be equal to negative 3 times 6 is negative 18 sine of 6x. The second derivative of our function, y double prime, will be equal to negative 18 times, once again, the derivative of the inside of our sine function, so times 6. And when we take the derivative of sine, we get cosine back of 6x. And so our second derivative is going to be equal to negative 108 when you multiply 6 times 18 times the cosine of 6x. We can then go ahead and plug our initial function and our second derivative into the tested differential equation, and so we have 36 times our function y, 3 cosine of 6x, plus our second derivative, which is negative 108 times the cosine of 6x. Multiplying 36 times 3 will give us positive 108 cosine of 6x minus 108 times the cosine of 6x. And so we can see that this function minus this function will give us a value of 0, which is what we expected our differential equation to be equal to. And so we have verified that the indicated function is a solution for the given differential equation. For our next problem, we need to verify the differential equation x squared times the second derivative of y plus x times the first derivative of y minus the original function y all over 2 is equal to the natural log of x. Our function y is given as 3x minus 2 times the natural log of x. We begin by writing out our initial function y is equal to 3 times x minus 2 times the natural log of x. The first derivative of our function, y prime, will be equal to 3 minus the derivative of the natural log of x is 1 over x, and so we have 2 over x. The second derivative of our function, y double prime, 3 disappears when you take the derivative of a constant, minus 2 over x, if you use the quotient rule, becomes positive 2 over x squared. And so we plug these functions into our differential equation. We have x squared times the second derivative, 2 over x squared, plus x times the first derivative, 3 minus 2 over x, minus the original function, 3x minus 2 natural log of x, all over 2. Multiplying x squared times 2 over x squared will give us a value of 2, plus 3 times x, so plus 3x, minus x times 2 over x, so minus 2, minus distributed to 3x, minus a negative 2 natural log of x, and so we have plus 2 natural log of x. This value is all still over 2. We can then cancel like terms. 2 minus 2, positive 3x, and minus 3x will all cancel out. And so we have 2 times the natural log of x over 2. The 2's cancel, and our result is the natural log of x, which was the expected solution of our differential equation. And so we have verified that this function is a solution of our differential equation. For our next problem, we have been asked to find the values of r such that the equation given is a solution of the given differential equation. The given differential equation is 7 times the second derivative of y needs to be equal to negative 7 times the derivative of y plus 5 times y. We begin by writing our initial function y is equal to e to the power of r times x. We can then take our first derivative, y prime, is going to be equal to the derivative of the exponent, so we have r times the original function, e to the power of r times x. Repeating the same process and taking the second derivative will give us a value of r squared times e to the power of r times x. Plugging these derivatives and the original function into our differential equation, we get 7 times r squared times e to the r x power needs to be equal to negative 7 times r times e to the rx power plus 5 times e to the rx power. Simplification of this equation gives us 7r squared times e to the rx power is equal to negative 7r plus 5 times e to the rx power. We can cancel out the e to the power of rx on both sides of our equation, and so we get 7r squared needs to be equal to negative 7r plus 5. Moving everything to one side of our equals sign, we get 7r squared plus 7r minus 5 is equal to 0, and so we have a polynomial, and we can use the quadratic equation to solve for our values of r. Using the quadratic equation, you get negative 7 plus or minus the square root of 7 squared minus 4 times 7 times negative 5. This is all over 2 times 7. Multiplying terms and squaring terms where appropriate, we get r is equal to negative 7 plus or minus the square root of 189 all over 14. And so by taking both the positive and negative values, the final answer is r equal to 0.482 or r equal to negative 1.482. For our next problem, we need to verify that the indicated function is a solution of the given differential equation, and also find a value of the constant c to satisfy the given initial conditions. Our function y of x is equal to the constant c times e to the negative 7x squared power. Our differential equation is the first derivative of y plus 14 times x times the original function y needs to be equal to 0, and the initial condition is that y of 0 must be equal to 14. And so we begin by writing our initial function y of x is equal to the constant c times e to the negative 7x squared power. We can then take the first derivative of this function, y prime of x, and find that it is going to be equal to c times negative 14x, the derivative of our exponent, times the original function e to the negative 7x squared power. Plugging the derivative and the original function into our differential equation, we find that c times negative 14x times e to the negative 7x squared power plus the original function, or 14 times x times the original function, is going to be 14 x c times e to the negative 7x squared power. Bringing this negative out front, we see that the first term cancels the second term, and so we get a value of 0, which is exactly what we expected our differential equation to be equal to, and so we have verified that the function is a solution. We can now solve for the given initial conditions. Y of 0 must be equal to 14, and therefore 14 must be equal to the constant c times e to the negative 7 times 0 squared power. This is equal to c times e to the 0 power, and this is equal to just c, which must be equal to 14. And so we have found that the value of our constant c must be 14 to satisfy the initial condition y of 0 must be equal to 14. For our last problem, we have been asked to identify by intelligent guess a function that is a solution to the given differential equation. We can begin by taking the differential equation that we are given, the first derivative of y minus 4xy equals 0, and slightly manipulating it using algebra. And so we can change it to the derivative of y prime, must be equal to 4 times x times our original function y. Given that we know that the derivative of e to the power of a function f of x is equal to the derivative of the function in our power f prime of x times e to the f of x, we can see that if our y is some function e to the power of some function, we can find what the derivative of that function is, and it needs to be equal to 4x. So f of x may be equal to 2x squared, in which case f prime of x will be equal to 4x. And so if y is equal to e to the 2x squared power, we find that y prime of x is going to be equal to 4x times e to the 2x squared power. And if we plug our function and its derivative into the original differential equation, we find that it is equal to 0. And so we have found a function that is a solution to the differential equation, y equals e to the power of 2x squared. For our next problem, we are given x squared times the second derivative of y minus 2 times the original function y must be equal to 0. We can once again manipulate this equation using algebra, and so we get x squared times the second derivative of y double prime must be equal to 2 times y. If we divide both sides by x squared, we get y double prime must be equal to 2y over x squared. If we assume for a moment that y is equal to x squared, y prime would be equal to 2x, and then y double prime would be equal to 2. And if we plug y is equal to x squared into this equation, x squared over x squared would give us a value of 1 times 2 would be 2, and so we get y double prime is equal to 2, and it appears that this function will be a solution. Plugging the second derivative in the original function into our differential equation, we would get x squared times 2 minus 2 times the original function x squared. And so we get 2 times x squared minus 2 times x squared, which is 0. And we have verified that the function y is equal to x squared is a valid solution of the differential equation x squared times the second derivative minus 2 times the original function equals 0. That concludes this video on simple first-order differential equations and mathematical models.